All right, guess I'll go ahead and get started. Hey everyone, thanks for joining us today for our webinar, Online Chlorine Measurement Technologies. My name is James Lunsford, and I'm the National Sales Manager here at Chemtrac. For more than 40 years, we've been a leading manufacturer of water quality instrumentation. We help treatment plants across the world optimize processes, maintain their regulatory compliance, and reduce their operating costs with reliable online analyzers, including residual chlorine measurement solutions. Online chlorine monitoring is essential for effective disinfection control, protecting public health, meeting regulatory requirements, and running a more efficient operation. In today's session, we'll walk you through the current technologies available, how they work, the key differences, and practical considerations to help you evaluate the best approach for your plant. Here's how it's going to flow. Timothy is going to deliver a focused 30-minute presentation for us, covering the technologies, the applications, and best practices. After he's done with this presentation, we're going to open up the floor for a Q&A. I'm going to moderate that. And after we're done with the webinar today, a full recording is going to be available on demand. And we can send that out. We'll send it out shortly after. You can review that and share it with colleagues. I'd now like to go ahead and introduce our presenter. Timothy Woolley is our Southeast Regional Sales Representative. He works closely with water and wastewater plants across the region and brings strong technical knowledge of online water quality instrumentation. Timothy, the floor is yours. Go ahead and take it away whenever you're ready.
All right. Thank you, James. Thank you, James. Very happy to be here. And I'm going to go ahead and get started on today's presentation on online chlorine measurement technologies. As James said, if you had questions during the presentation, feel free to write them down, save them to the end, or you can put them in our chat, and we will get to them at the Q&A portion. So a little bit about what we're going to talk about today. Today, we're starting with all the types of disinfectant monitoring that Chemtrac offers. We'll move into a bit of specifically the online chlorine measurement technologies and the common ones that are used and how we use them in water treatment. We'll get into a bit of the scientific background of how these chlorine measurement technologies work and go through the different types that we offer. We'll talk about pH a bit and how pH affects chlorine detection in water and why we use things like buffers to put in those chlorine probes to help them better detect the chlorine in the water. We'll talk about where do we test in water treatment, at what points throughout the water treatment process we test, and why we do that. I'll show you a bit of performance data that we've collected in the field so that we can see real-world examples of how these chlorine probes work. We'll talk a bit about the setup and calibration of these chlorine probes, just some practical advice for operators, whether you already own chlorine probes in your plant or are thinking about adding chlorine. And then we'll talk a little bit about other applications aside from municipal water treatment where chlorine can be used in the water treatment plant. And then at the end, as we discussed, we'll have plenty of time for questions. So these are the different types of chlorine disinfectant or disinfectant monitoring that we offer. That does include chlorine here on the left. You'll see our HydroAct analyzer as well as an example of a chlorine probe. A close-up image of a chlorine probe here, as well as a chlorine dioxide probe. We also offer things like ozone. That's not pictured here, but we'll speak about ozone later in the presentation. And you see both free and total chlorine, colorimetric, and amperometric probes. And I'm going to talk a bit about the differences between those two types of chlorine measurement technologies. So beginning on the left here, the amperometric probe, we often call that the reagentless probe because it does not use reagents. That's a membrane-covered chlorine sensor. It has no moving parts within it. It has no bottles of reagent to change out monthly, and it has very easy maintenance that typically is done quarterly. Both the free and the total amperometric chlorine sensors will look like that on the left. Visually, there's really no distinction between them, but the way they detect chlorine in the water will be different. On the right, you can see a Chemtrac DPD chlorine analyzer. We often call that technology colorimetric because it senses chlorine via a color change in the water. We have Chemtracs next to another commonly used DPD analyzer. Those use a color change, as I said, in the water to detect the concentration of chlorine. They use a 515 nanometer emitted light that shines through a sample of chlorine that has a indicator chemical put in it. The reason we call it a DPD, that stands for N-diethyl p-phenylene diamine, and it's much easier to just say DPD. And so those DPD chemicals react with chlorine in the water, and we're going to get in a little bit later on the specifics of what that looks like and what's actually going on within that probe. And so starting off with our reagentless chlorine analyzer, that's the same thing as amperometric. That typically has very good performance, less than 1% of drift per month in its reading. We do have an excellent track record of EPA method 334.0 compliance. And I will get into a little bit later about the specifics of that EPA method, when it came about and why it's so important in chlorine monitoring. These do have a reduced pH dependency. So these technologies have a buffer chemical within them made up of a weak acid-base pair that allows it to perform well even despite fluctuations in pH. And I'll show graphs a little bit later that kind of demonstrate how pH affects chlorine readings in the water and why it's so important to have something like that. As we covered, these have no reagents, no moving parts within them. We have a once per year membrane replacement and about a once every 6 months to a year replacement of the electrolyte that goes within that membrane. These come from our warehouse. They can be set to detect both free or total chlorine. The price is the same of those, whether you're purchasing both free or total. And they all come with a 1 year warranty. Most of our products do come with that 1 year warranty coverage, but we expect them to last quite a while. We have these amperometric reagentless chlorine probes in the field that with proper maintenance and exchanging of the consumables, they can last well over 15 years. So let's move on to some advantages and disadvantages of these two types of technologies. Starting off with amperometric, which is what we just saw right here, reagentless. Those are truly continuous measurement. And what we mean by that is that it's online all the time. Both of these technologies are online. However, the reagentless one is constantly reading changes in chlorine. So if you're trying to keep up with very quick changes in incoming chlorine at your plant, this might be the way to go. They have very low maintenance, about once per year, as we said, for the membrane, and generally once every 6 months, you want to change out that electrolyte. And that is something that pretty much anyone that works at a plant can do. We are able to teach that really quickly. We'll go over the electrolyte changing. But those of you that own these type of probes have probably done it yourself before. They have no chemical reagents, which is a huge benefit. Not only does that save money, but it avoids the headache of having to change out those reagents and potentially dealing with the danger that comes with those reagents. These have no tubings to replace because there's no tubing for reagents to move through. And you can calibrate or input proactive maintenance warnings. Those are built in on our HydroVac system that will alert the operators or those working within the plant when you need to change out those consumables. A couple of disadvantages of this technology is that they can read a false zero. This means that if you're going to be putting them into a application where there is no chlorine in the water, these might not be the best fit. You want to have at least a small amount of chlorine in the water at all times to best take advantage of these, the great performance of an amperometric probe. And I have in here validation against approved lab unit about once a week to maintain optimal accuracy. And it's important to note that this once a week calibration is really only needed if you are reporting to any sort of regulatory agency. Oftentimes the EPD, but any regulatory agency that you need to report to might require once a week validation against a benchtop DPD analyzer. Typically, if you're not using these for regulatory or reporting purposes, they can last up to, we advise about 1 month before calibrations or verifications, but it can go easily up to 6 months without calibration and still remain within a very acceptable range for chlorine detection. Also, it's important to note that the the DPD units also will need to be calibrated at the same frequency if you're using them for reporting purposes. So those both have that same disadvantage there. So colorimetric, moving on to our DPD colorimetric probes. As we said, those are detect the chlorine via a color change in the water. This is it's an extremely commonly used method. I would say the most commonly used method. And it is the same method as a handheld reference. So if you have a benchtop unit in the lab that you're verifying things against, this uses that same DPD colorimetric method to measure chlorine. And these typically do not have the false zero reading issue. So these are better fit for dechlorination applications or times where there might not be always chlorine in the water. A few disadvantages, we would say, of this type of technology is that they do have more maintenance. So typically you would need to replace these reagents monthly. You purchase and replace them. These reagents do expire, so they cannot be stored forever. As we covered, need to change out that pump and tubing that pumps those reagents into the water. And these reagents do have the potential for things like skin, eye, and respiratory irritation. So it's important to be careful when handling these reagents. They do present a bit of a safety hazard. And the last thing I want to talk about is that they are not truly continuous. These measure chlorine about once every 2.5 minutes. Um, and you can go about 2.5 minutes between the times it reads, which is typically for most applications perfectly acceptable. You typically don't need to read more than 2.5 minutes or quicker than that, but if you do, the amperometric chlorine probe is provides that great advantage. One more advantage of this that I haven't mentioned yet was that other oxidants like bromine, iodine, ozone, chlorine dioxide, incoming in the water, those might actually affect the chlorine readings of the DPD probe. So in those applications, you might want to use the amperometric probe instead. But typically in most water treatment applications, that's not something that you really need to worry about. So this is a great slide we put together on the cost analysis if you're thinking about purchasing an online DPD or amperometric probe. We'll start on the left here with the online DPD. That's our HydroAct 2 with the DPD analyzer. You can see that does start with a bit of a higher initial cost, about 6,600 to purchase that, and it comes with 1 month of reagents. Then you get free or total reagents at about $105, and those need to be replaced monthly. So you'll see that cost breakdown. After 1 year, you purchased 11 months worth of reagents because it comes with 1 month included. After 2 years, you're going to be replacing about 1,200 worth of reagents in those following years. And as you can see, that adds up pretty quickly. We have about over $12,000 after 5 years would be your cost if everything is performing well, which we do expect it to. Comparing that to the amperometric probe, it does have a lower initial cost, about 6,100, and that comes with a membrane and electrolyte, which will be good for about a year to 2 years. And then replacing those is about 295 for the membrane, about 160 for the electrolyte, but those will need to be used or replaced much less often. So putting you at about 6,600 after 2 years, and anywhere from 7,650 to 7,900 after 5 years, depending on the expiration of those electrolytes. Which is obviously it adds up much less quickly. So you're saying if you're planning on investing in one of these technologies out in the field and they're going to be used for 5 years or more, the amperometric, if it is fit for a good application, might be the way to go. So now I'm going to spend a moment and talk about the hybrid DPD analyzer. This is a newer technology. It's been out for about 1.5 years now from Chemtrac. And this has the advantage of combining the best of both worlds of these technologies. It uses this DPD method, the colorimetric method, to get immediate accurate readings right out of the box. It can self-calibrate using that DPD data, so there is no need to calibrate it against a benchtop DPD unit. And once it's stable, it switches to that amperometric reading. This means that the DPD analysis can be much less frequent. It can only use its DPD about once per hour, which greatly extends the life of those reagents. And it's important to note that these do use a separate type of reagents than the other DPD analyzer. These are a longer lasting reagents that could have a shelf life of up to a year, which makes them a perfect fit for this hybrid DPD analyzer. And we typically include 6 months worth of reagents when this is shipped. And so this is great to have out in the field, maybe in distribution where it can self-calibrate, but it also can go longer between needing maintenance. This hybrid cost initially is a bit more because it combines both of these technologies. It's just over 11,000 to purchase new. But as we covered before, because of its advantage of needing to replace the reagents much less, that can result in plenty of cost savings over time with extended use. So I'm going to get into a bit of how does it work? How do we actually, how these technologies actually work for both amperometric and DPD? Here's a close-up picture of an amperometric probe, showing the membrane, showing the electrodes in there. And I'm going to show a diagram later on of what this looks like on a more molecular level. But you can see on the left here, here's a diagram of how you would actually position this probe within a flow cell. So we have the water flowing through across the tip of that probe, leading to an atmospheric drain at the end. And all you need is a constant flow of water across the tip of that probe to get an accurate chlorine reading. In the presence of chlorine, these have an electrochemical reaction that takes place. They actually have a charge that's moving across that water. And the intensity of that charge reflects the change in chlorine concentration. Here's a good diagram of how both of these work. So starting on the left with our amperometric probe, you have our current 3-electrode design. And this small arrow here that you see going from the counter electrode to the working electrode, that represents the current flowing through the water. And the working electrode is actually what picks up that current to detect the amount of chlorine in the water. On the right here, we have the colorimetric method. And this is a great diagram. It shows how an oversimplification, of course, the water comes in, you use a buffer to compensate for pH changes, and you use that indicator, which is when it reacts with water is typically pink in color. And so inside this glass cell, you can actually see a color that might be similar to the color that you would get when it is sensing that chlorine in the water. You have a light source shining through that water, and it goes to a photodetector that picks up that light. And depending on how much light passes through and the color or intensity of the color in the water, that represents the proportionate amount of chlorine present in that water. But in order to work, it does need the addition of that indicator and that buffer to accurately detect chlorine. As we said, this is a tried and true method. It's used pretty much all across the world, and it is known to be very reliable. I'm going to talk a little bit about our standard 2-electrode design. This one is currently not in production. We've moved on to this 3-electrode design that I showed earlier. But many chlorine probes out there that are amperometric do still use this 2-electrode design. And some advantages or disadvantages of this is it does do that online continuous measurement, but it is susceptible to zero drift, which is zero drift is a change in the zero reading of the analyzer that is apparent when the sample is completely free of chlorine. So sometimes it can over or under detect the chlorine in the water when it should be reading zero. And some of the competition does still use this particular design. So in applications where there is constant chlorine, you might not encounter this. Although the addition of a counter electrode, or the reference electrode here that we have in the 3-electrode design, all but eliminates that zero drift. And this one has a consumable electrode. So because of the strain that's put on these, the electrodes themselves might need to be replaced, and it might have about a 5-year life, as opposed to the 15 plus, maybe even 20-year life that we discussed before with the 3-electrode design. So here's a 3-electrode design again. It uses that potentiostat 3-electrode design, and it is a very stable reaction that has virtually zero drift. So this has a significant improvement in its accuracy and a much longer life of the electrodes. So we do still have this technology that's been out in the field for over 15 years and is still working accurately, just with proper maintenance and proper exchange of the membrane and the electrolyte. This long life is just a huge practical benefit to operators or anyone working with these probes out in the field. So here's a bit of a closer look at what's happening inside of the tip of those probes. So you see OCl, which is hypochlorite, that's present in the water at a greater concentration when it's simply existing in chlorine in the water. After it passes into, and I'll show you that little animation right now, when it passes through the membrane and mixes with that electrolyte that we have within the membrane, it transforms into a HOCl or hypochlorous acid dominant compound. And that hypochlorous acid is actually what is read by the probe. This is a bit of an oversimplification because both OCl and HOCl are both present in the water at both points during this reaction. However, the conversion of a hypochlorous acid dominant I would say solution, is what is necessary to accurately read the amount of chlorine in the water. So an important component of this is that electrolyte gel. And that electrolyte gel exists at a pH of, we show here under 6.0, and that lower pH concentration is needed to get an accurate reading. This is critical for the sensor's ability to measure that chlorine accurately. The working electrode and the reference electrode require that conductive medium to allow the tiny current needed for measurement. That's typically pico to nanoamperes of current. An electrolyte gel that provides a semi-solid medium that conducts ions while preventing the loss of electrolyte through that membrane. If we were to use something that was more non-viscous, something more runny, for example, water is able to pass through that membrane, and that's very intentional. You need something like water to pass through that membrane to mix with that electrolyte to allow for that current to pick it up. But this is a very tried and true technology at this point, and I will show you now why we do use that electrolyte gel within the membrane. It's important to make sure that that's screwed on very tightly. You retain all that electrolyte gel within the membrane because that allows you to get a more accurate reading and not have any of that leak out into the water. So here's an example of why we use this buffered electrolyte. So you'll see this pink or purple line here showing a non-buffered electrolyte. So when that is used, when the pH rises in a sample of water, you have a decreased response from the probe to that free chlorine. In this case, it's going to be free that we made this chart for. And that decreased percentage response is going all the way from 100 to pretty much zero when you get to above a pH of 9. But with the use of a buffered electrolyte, which is included with all these chlorine probes, it greatly resists those pH changes. That neutralizes those acids by having a weak acid-base pair, and that keeps the environment stable even as those reactions occur. This stability is just very necessary to ensure that the probe signal is reflecting a change in chlorine and not a fluctuation in pH. This next graph I'm showing you here kind of shows what those fluctuations in pH do when it's picked up by a chlorine probe. So on the top here, this blue line represents the incoming pH picked up by a probe, and you'll see the time as it moves across the bottom here. And this pH, when it spikes, it results in an inverse reaction of the chlorine probe. This red line here is a competitor non-buffered electrolyte, showing you how when chlorine dips, when pH dips, you see a spike in that response from chlorine. And those can be very drastic, just as drastic, if not more so, than the actual change in pH. And now when using a pH buffered chlorine probe, such as Chemtrac, here's that's demonstrated by the green line right here. You still do have a slight response to the changes in pH. It's nearly impossible to prevent it entirely, although with the pH buffer, it's greatly reduced. And you can see that that is in direct relation to the pH buffered electrolyte that we put in this graph. It resists those changes in pH when it's put into that chlorine probe. So I'm going to move a bit into water treatment application. So where do we test in water treatment and why? Pre-oxidation is one. It's slightly less common, but it is an area where we would add disinfectants. So we can put detectors for free chlorine, total chlorine, chlorine dioxide, or ozone. By removing these contaminants before you get to the main treatment process, this enhances the overall efficiency of water treatment systems. Chlorine is incredibly effective, as we all know, in removing things like germs, but also soluble iron and manganese, as well as organic micropollutants. However, it can produce harmful disinfection byproducts, or DBPs, we call it, when it's reacting with this natural organic matter. So for this reason, some water treatment plants might choose to not add chlorine at this step of the process or add something like ozone at this point in the process because it reduces the risk of creating those DBPs. And I think it's important to stop here and discuss a bit of DBPs. How are they formed and why do we want to avoid them? So DBPs are disinfection byproducts. They form when chlorine reacts with the natural organic matter in the water. This could be things like decaying plants, algae, any other carbon-containing compounds. DBPs are not only a risk at the beginning of the process, they can be a risk at any point in the process, but obviously at the beginning of this water treatment process is where you see the most incoming DBPs. So wherever you are disinfecting, DBPs can form. They react with the chlorine in the water, and this can contribute to things like trihalomethanes, haloacetic acids, which we call THMs and HAAs. Those are the most commonly encountered DVPs. And the EPA has set limits on these commonly encountered DVPs due to their link to cancers, liver and kidney damage, as well as reproductive harm. So because we have this known linkage to these risks, it's important to monitor these things in the water, and it's important to monitor your amount of chlorine and where you're adding it. And of course, the EPA has set limits on it for obvious human health reasons. So back to the most common area to add chlorine to the water. That would be in your finished water here, the disinfectant. You can see in our process out at the bottom, it's right after the clear well. But this is just one example of where you add chlorine in the water and where you might need to use chlorine probes. These probes can test for a whole mess of things right here. So this is probably the most common place that we use chlorine probes in the water. And then a bit in distribution. So obviously we have chlorine probes out in distribution. We need to retain a certain amount of chlorine in the water to ensure that when this water is going to people's homes, it has an adequate amount of chlorine to ensure that it's disinfected throughout the entire process. So this is where a large number of chlorine monitors would be installed, specifically the amperometric probes or hybrid DPD probes, things that might be maintenance free or require less maintenance than something like an online DPD probe. Now I'll talk a bit about this chart. This shows a tracking of Chemtrac's amperometric chlorine analyzer over about 2 weeks in April and May. This came from 2013, but it does a great job of showing its comparison against an online amperometric probe. During this test here, it was actually not calibrated again for the duration of this test. And as you can see with an initial calibration, even without further calibrations throughout this 2-week period, it follows very closely to the benchtop DPD unit. A bit more in depth about this EPA method 334.0 that we discussed earlier. This is, it came out in about 2009, I believe, and it was used to allow water treatment plants to use these online residual chlorine analyzers like DPD and amperometric probes for reporting if it can pass the IDC, which is the initial demonstration of capability. This requires that after calibration, the analyzer needs to stay within about plus or minus 0.1 milligram per liter, or plus and minus 15% change, whichever is greater, of a grab sample measurement. So that grab sample would be the benchtop DPD unit that we talked about. And it has to remain like this for 14 days. And as we said earlier, it needs to be verified against a benchtop unit about once a week if you're going to be using it for these reporting purposes only. This is a graph that's showing how these perform. In this example, it was a 4-month test, and the unit was calibrated at the start and then allowed to run, and no further calibrations were performed again. In this example, our unit, which is shown in this gray line in the center here, it stayed well within the 15% range required by the EPA method 334. And that 15% range is demonstrated by these dotted lines here above and below. We have another DPD unit shown in this orange right here. And then we have the grab sample shown in blue. And as you can see, all of these follow very similar trends. Typically, you wouldn't see a deviation to this degree. The reason that by the end of this process there was such a deviation is because this was a 4-month test and it was not calibrated throughout the entirety of this 4-month test, simply to prove that even without calibration, these technologies can stay well within the plus or minus 15% range required by the EPA. So let's get into a bit of setup and calibration. So this is what you would need to worry about if you're actually setting these up in a water treatment plant. So this is our startup curve, and this is showing when an amperometric chlorine probe is put online, when you use one of these reagentless probes, it takes a bit to stabilize and acclimate to the water that it's put in. And the red line on top is showing the actual amount of chlorine in the water, and this blue line is showing the chlorine reading that's output by the probe. And so if you give it enough time, generally about 6 hours is what we recommend, but really overnight for a second calibration. To do that initial calibration, you need to wait for that acclimation period. So we typically say anywhere from 4 to 6 hours before the first calibration, and then wait a full 24 hours, wait overnight to ensure that the reading has acclimated fully. Then you can do that second verification or calibration to the probe after it matches the chlorine in the water. And you really only need to do this whenever you put the chlorine analyzer online or when you replace all those consumables on that chlorine probe. A bit about calibration and maintenance. And so after this probe has stabilized, you perform that DPD measurement and you compare it against a benchtop unit, and that will give you this calibration slope. And this calibration slope here goes from 4 to 20 milliamps. And that might be familiar to a lot of you that work with SCADA systems or work in water treatment. We do typically use this 4 to 20 milliamp value that's reported to our hydrovac controller. And if needed, it's also reported to a SCADA system. At the minimum here, you have 4 milliamps, the max being 20. Um, and you can set it for a chlorine probe that detects anywhere from 0 to 5 ppm of chlorine. You'd put 4 at 0 ppm, and 5 would be programmed to 20 milliamps. When you initially calibrate this, this is what the slope should look like. And as that electrolyte ages within the probe, that slope is going to flatten out. And typically it needs to stay within this green area on the graph that is put here. And that calibration slope stays within that verifiable range. When it flattens out fully or gets below, let's say 10 milliamps would be the max, 4 to 10, then you know that you need to replace the electrolyte within that probe. And when you do replace the electrolyte in the membrane, it should get right back on track with a full scope of 4 to 20 milliamps in value. Um, all of our chlorine probes, a lot of the newer ones, they all show a probe health. So typically, operators can pay attention to the probe health readout, and that needs to remain greater than 50%. Anywhere between 50 and 100% represents good probe health, and that should give you a good idea of when you need to replace the electrolyte and the membrane. Here's a quick graph or a quick diagram of our flow cell design. This is a non-pressurized flow cell. This is able to minimize pressure fluctuations at the membrane. It leads to an atmospheric drain at the end. That simply means that the drain is at atmospheric pressure, which has the water draining out without the use of pumps. Um, and it's a vented design. That vented design right here, you see it's just open to the air. So that if you do have something like a sudden spike in incoming water pressure, that vented design allows it to overflow out the top, which is much preferred to that spike that comes in water pressure, which could lead to a spike in chlorine readings. It could also potentially lead to damage to that sensitive membrane. So it's better to have a bit of overflowing water than to risk potential damage to the probe's membrane. Here is a pressurized flow cell design. Now, most other companies, a lot of them do use this pressurized flow cell design, which can work just fine if you have a very consistent incoming pressure. Um, but this can result in fluctuations at that membrane. So this could produce unstable or less accurate readings. Typically, it's not needed when you're using chlorine, but we do offer it for other types of probes that might need a closed flow cell design. So this optimal water pressure that's coming across it is typically anywhere from 250 milliliters a minute to 1,000 milliliters a minute of flow. Typically 500 is ideal. Anywhere from 500 to 700 is perfect. And the reason you want to maintain this adequate amount of flow, this flow rate, is to, well, for one of the many reasons, is to ensure that the membrane is going to remain in good health, ensure that it's accurately reading, and to prevent bubbles from forming on that membrane surface. Here, these pictures show when it is installed a chlorine probe that might be placed a little bit too high or a little bit too low, and you want to have that flow going directly across the membrane surface. This prevents bubbles from forming on that membrane surface, which could result in inaccurate readings. Now, one thing I wanted to mention is that typically older probes, maybe 2 years or older, if they were installed before then, you would need to worry about this particular positioning of the collar on the chlorine probe that allows it to be placed at this particular height. With our newer probes, they come with a fixed collar. It kind of has a C-clip that fixed onto this collar that allows you to just drop it in and then it will automatically be placed at the optimal height for a flow cell. So when you're using it with a Chemtrac flow cell, with a Chemtrac probe, typically you don't need to worry too much about the height at which it's positioned. As we said, 250 to 1,000 milliliters a minute, that's the optimal flow rate. And ideally, if you're using one of these amperometric probes here, you want to have a constant flow of chlorinated water that leads to that atmospheric drain. If there are large changes in pressure, we recommend installing a constant head device or a pressure regulator, for example, a dole valve, to make sure that there aren't incredible spikes in incoming water pressure or losses of pressure that could lead to inaccurate chlorine readings. Here's just an example of a typical installation. Um, we do offer demo units available as well, and they will come mounted on a back plate like this. But you can install this at a back plate in a water treatment plant. A lot of you may be familiar with this if you have these chlorine probes in your plant. And this is showing the newer design that has a fixed collar around the chlorine probe, which automatically allows it to be placed at an optimal height to have that water introduced to the membrane. A couple other available options for amperometric chlorine probes would be single, dual, and triple flow cells. So you can see here, you can put one, two, or even three probes in line with one another that can read from the same water sample. You could add pH to it, chlorine, you could put free and total chlorine within the same water sample, as well as things like ozone or chlorine dioxide. Chlorine dioxide, both of those probes fit well within these flow cells, and they can all detect the same sample of water. Now I want to talk a bit about here the applications for these chlorine probes that might be something other than municipal drinking water treatment. So wastewater treatment is, of course, another area where you might need to add a disinfectant. And this final effluent disinfection can use total chlorine probes to detect that chlorine in the water as it finishes with wastewater treatment. Um, Also for dechlorination applications, when you need to get all the chlorine out of the water, maybe before it's being put back into a water source, you can use our DPD analyzers or any DPD chlorine analyzers to ensure that all the chlorine has actually been removed from the water, because there are applications where that can be extremely important. A bit about our hyposense. So this is a sodium hypochlorite probe, also known as bleach. And this can measure sodium hypochlorite concentration from 0 to 16%. This one has an optical sensor. It does not include any reagents or consumables, so it is kind of a one-time purchase. And it is specifically engineered to withstand harsh environments that are associated with the use of industrial bleach. So you don't need to worry about any sort of corrosion when it is immersed in bleach. It does a very good job of remaining intact and giving an accurate reading of sodium hypochlorite. A bit more about their hyposense. So some applications for that might be measuring incoming deliveries. When you have incoming deliveries of sodium hypochlorite, you can verify that they actually are delivered in the concentration that was ordered by using this sodium hypochlorite probe. As we know, sodium hypochlorite does degrade over time, and it degrades more quickly when it is in higher concentrations. So oftentimes, for these industrial applications, it is diluted once it gets to a plant, and this dilution helps make it last longer over time. And you can use this hyposense probe to make sure that you're diluting it to the intended strength, and also make sure that it does not degrade too much in between shipments. Or maybe it does, but either way, the hypochlorite probe will allow you to detect that when you're ordering bulk sodium hypochlorite. So this can measure that degradation between deliveries and ensure that you're getting what you pay for when it comes to sodium hypochlorite shipments. Um, I want to move on a little bit to another application you could use these disinfectant technologies, specifically free and total chlorine, would be used for things like pool spas and splash pads. A little more fun of an application, but equally important to monitor the amount of chlorine in the water for public health and safety when you're using it in things like pools and splash pads. And this pretty much concludes this presentation today. I'm going to open up the floor to questions that we might have, and both James and I will be available to answer these questions. So, James, I'm going to give it over to you to see if we have any questions that have come in.
All right, thanks, Timothy. It's a great presentation. A good overview of the measurement technologies that are available out there. We are moving on to that QA portion right now, and I'm going to have our senior product specialist, John Clark, come in there and join you to help with some of these questions. We had some
Sure.
great ones come in, so he'll be joining you in the conference room in just a second there, Timothy. And if y'all have any additional questions, I'm going to go over some of these that we got in one of our chats. You can put those in the Q&A box down at the bottom of your screen, and I'll review them and I'll pass them over to John and Timothy after I have reviewed them, and we'll try to get to as many as we can. If we aren't able to get to your questions, we will be available afterward, and we'll have the email address where you can email us any of your additional questions. So I'll go ahead and get started here. I'm going to start from the top and work my way down. And this is a great question, this first one. It's one that we get quite frequently. And it's asking about amperometric methods. How accurate are they in detecting monochloramine? And I know that that's going to be dependent on a few things. So I'll let John go ahead and answer that one for us.
Yeah, thanks, James. And yeah, it's a great question, and it's an important question. The one thing to keep in mind is with amperometric probes, they are going to have a little bit more sensitivity than DPD if the species of chlorine changes. So they are more species sensitive. As long as you're maintaining the proper ratio of ammonia to chlorine, which is approximately about 4:1, and as long as your pH is in the optimum range for chloramination, around 7.5 to 9, you're going to be predominantly forming a stable monochloramine species, and these probes will maintain accuracy extremely well when it's in that environment. Where you can run into issues is if your pH drops, down below 7, or if you're not maintaining the right ratio. If you start going 5 parts of chlorine to 1 part of ammonia and exceeding that limit, you'll start getting into break point. At that point, you can start forming dichloramine. Our electrolyte, our probe does use a potassium iodide, similar to how DPD works. It's actually free iodine that we're measuring, or iodine. But the problem is with membrane covered probes, the membrane permeability, the kinetics are a little different than DPD, and you will see more of a degradation in response compared to DPD. Now, we actually have an instrument called the hybrid analyzer, which is another technology that we talked about. And it's a great tool to use in those kind of applications because it kind of gives you the best of both worlds. You get the performance and the continuous measurement from the total chlorine probe, but still have the DPD there as a backup in case you run into any kind of issues with not being able to maintain, proper parameters for chloramination. But hopefully that helps answer the question. So again, for 99% of the chloramination applications out there, the conditions are being met pretty much all the time. So it's not too much of a concern. But yeah, if you do notice that you're not maintaining proper ratio of chlorine to ammonia or the pH, that could be more of a concern.
All right. Thanks, John. That was great. The next one's a pretty easy one. We went over it just a little bit in the presentation. It's asking what pH is acceptable for the amperometric probe, and can it be used with water that has a higher pH around 8.5 to 9? I can go ahead. What I have seen out in the field quite a bit is we are good up to a pH of 9 on free chlorine. The biggest thing that you don't want to see are large fluctuations in your pH. So if you're seeing it fluctuate from about a 7 to 9, you will see some changes in your reading. But if we stay stable around that 9, we are able to get accurate readings with the free and definitely with the total. Do you have anything to add on that, John?
No, I mean, obviously the total can go up to a higher pH than the free, which upwards, I think the upper limit's 12 on that probe. And if there are situations where your application, let's say it's free chlorine and you are seeing large swings in pH, like say 7 to 8.5, that's the one situation where we would recommend our pH compensation feature. Typically, it's not needed. We very, very rarely need to utilize pH compensation with our free chlorine probe. But if the swings get large enough, then yeah, it can definitely help to improve the accuracy. And the big benefit with our pH compensation is because we're not compensating nearly as much as other types of amperometric probes. So our compensation factor is small compared to what you would get with some other traditional type probes, which don't have the electrolyte buffering capability that ours has. So it just means you're going to have better performance with pH compensation because we're not having to apply such a huge compensation factor.
All right, very good. Next question that we have here sounds like it's more of a wastewater question. And our probes, we do mostly in water, but this is one that we might be able to work with you on. If not, we might get you some more information offline. I'll let you decide how you want to handle this one, John. It's how's each technology going to help in detecting very low range? And of course, we'll probably be looking more at the DPD on that. They're looking at effluent discharge, total chlorine compliance, and how either of these will be useful in detecting free chlorine, monochloramine, which we already covered a little bit. DPD does a good job with that. Total chlorine, and it's going to be while in the presence of iron, manganese, and biological. So definitely sounds like a waste stream.
Yeah, it could be a bit of both. It's, when we say low range, it really depends on what we mean by low range, whether we're talking a zero point 0.1, 0.2, or a 0.005 milligram per liter requirement. Obviously, all the technologies struggle at some of these really low ranges that the regulatory bodies are requiring, like I said, the less than 0.01 type measurement results. But I'll just speak to some things here that kind of jump out at me is for wastewater effluent. When you're monitoring with DPD or ampermetric, there are some interesting things that happen, which to be aware of. One of those is like the other question we were talking about, chloramination. We essentially have chloramination going on in wastewater treatment. When we add chlorine to wastewater, there's usually sufficient ammonia there to drive it to monochloramine, but it's also a much more complex complex chemistry in the water. There's more types of organics that react with chlorine in wastewater than there is necessarily in water treatment in different types of organics. And you can form certain types of organics that do show up on, or certain types of organic chlorine species. They call them like organic chloramines. Some of these species can show up and interfere with DPD measurement. Whereas with the ampermetric probes, they're pretty much not, they're going to ignore those organic type combined chlorine species. So there's actually a paper out there from a competitor that talks about this, where if you have ampermetric and DPD side by side on a waste stream, sometimes you'll see the ampermetric dropping off, even though the DPD is holding relatively stable or not dropping off as much. And in those cases, if you do, what you want to do is a measurement, an actual DPD measurement of monochloramine, or using the method for monochloramine benchtop measurement, because sometimes what's happening is the monochloramine levels are dropping off and you're getting these other types of species which aren't as good at disinfecting your waste stream. So it's a kind of a complex thing to talk about, but in wastewater, there's more than just can it measure monochloramine. It definitely can measure monochloramine in wastewater, and we install them for that purpose all the time. The bigger issue we run into sometimes is that it's not matching with the DPD test. And when that's occurring, it's a good idea to do the monochloramine bench test and see if what's happening is if your monochloramine levels are dropping at the same time that your ampermetric total chlorine is dropping. Because if it is, but your DPD is not dropping the same, then that's suggesting you're having interference from these other types of species. As far as manganese goes, it's typically not a problem. We have applications where there's quite a bit of manganese buildup on the probes, and the chlorine can still permeate through that manganese buildup, and it doesn't affect the reading as much. Iron scaling, iron fouling on the membrane can be more problematic. So much just kind of depends on chemistry and what's going on. But that's one to be a little bit more cautious about. And biological, well, that kind of speaks to what I was talking about earlier, certain types of species that can form with organics or biological material, especially in wastewater. A bigger concern with the low level measurements, whenever you're looking to measure really, really low levels of chlorine, DPD is fairly reliable. And in some applications, that's definitely what we'd recommend if you're going to be running continuously at low levels, like less than 0.1. That's probably the better technology. Problem you can run into with membrane covered probes is you can start to get some biological fouling on the membrane, which can degrade the probe's response, especially if you have no chlorine in the water at all, and then a biological layer, biofilm builds up on the membrane. Chloramines will not penetrate that biofilm, and so it effectively can blind off the probe. So you have to be really cautious using membrane covered probes where you could have that sort of biological fouling occurring.
Yeah, thanks for all that, John.
Yeah.
Got a couple quick ones right here. I'll go ahead and knock these out. Someone had missed the beginning and they were asking how often the membrane electrolyte needed to be replaced. For the electrolyte, every 6 months to a year. For the membrane, every year to 2 years is our general guidance on that. And since you did miss the beginning, there will be a link sent out that has the full recording of this after the presentation. The other one was why is 50% health acceptable when we're looking at that calibration slope? And when we're looking at the calibration slope, that 50%, we're still going to have enough range there to get accurate, precise readings. What it does is that calibration compensates for wearing electrolyte. Once we get below that, there's a smaller range of that milliamp signal going back to the hydroact, and we can see the readings jump around a bit more.
Yeah, James, if I could jump in on that one too. I
Yeah,
always tell customers this is a very important feature, diagnostic that you want to look at every time you do a calibration. Our newer units do report a health percentage. You're not seeing it on this screen, but any units that we've sold in the last couple of years and any new units will report health. So you get it right when you do the calibration and you can see it. You want it to be greater than 50%. But what happens over time is if the membrane's degrading or the electrolyte's degrading, you'll see that health dropping. And so it's just an indication, a great indication of when you need to do service on that electrolyte or the membrane.
yeah, that's great. Then next one, another is either of these sensors, either the DPD or probe style sensor, NSF 61 rated. Neither of these two particular sensors are NSF 61 rated. All right. When do you need PRY and Dole valve? That's mostly going to be when you're seeing large pressure or flow fluctuations. If we have a pretty steady pressure and flow, they aren't needed. The ball valve that comes with the sensor is enough. We do have a 1 liter Dole valve that'll help control that, and that can any fluctuations that can handle that. And I would say almost all cases. All right. Do we have an option for a closed system with no waste stream on these two particular sensors? We do not, as far as I'm aware, John.
Yeah.
Okay. And then can the amperometric be used with peroxyacetic acid? I know we have a parasitic acid amperometric. I'm not sure about peroxyacetic
I'm guessing that's maybe what they mean, but
yeah, we do have the parasitic probe. Are there inline probes we would need are there inline probes so we wouldn't need a pump? Yes, that's true. They are in no, we don't have anything that's in line. Everything does require a bypass stream. And then with the combined unit, is there a constant reading between DPD measurement that could be used to drive the disinfection pump? And is the controller built in, or will we need a controller to run the pump? You want to talk a little bit about our PID controls that are available on that, John?
Yeah, and it's one area where Chemtrac really exceeds. Our controller has top-notch, PID control capabilities. I could talk. We could do another presentation on that. But essentially, every feature you would ever need to be able to automate dosing of chlorine, we have that built into the analyzer. So there's a lot of advanced features. So yeah, no concerns there at all. You do not need to outsource the PID control to a PLC, for any reason. And another thing I would like to tell on that topic is if you're using our Modbus communication protocol, the beautiful thing is you have read-write capability. So you can connect your SCADA to our analyzer and be able to change the set point, be able to turn the PID automatic manual. And we also have flow pacing. So you can set up for flow pacing, or you can have combined where it's doing, control on the chlorine reading and on flow both. So yeah, lots of great features there for control.
All right. Next one. Have you tested your probes in an environment with 0.2 to 2% organic solids, like a paper mill environment, to measure total or free chlorine? I'm not sure if we've measured anything with that high of an organics. John, have you seen anything?
Yeah, we definitely have systems in pulp and paper applications. Again, this goes to that whole thing about, some challenges sometimes with the types of species that are forming. So whenever you're comparing to DPD, it's a complex chemistry, and the type of species you're forming aren't just, free chlorine, monochloramine, dichloramine. There's all kinds of different things that can happen. So just one thing to be aware of is, you want to do a little bit more testing in the lab, kind of figure out what's going on, what species you're forming. You may find in a paper mill application, again, that the total chlorine probe doesn't exactly match with DPD, but that doesn't mean the total chlorine's wrong in that situation. Because you want to maintain a good disinfectant, you want monochloramine there. And in the total probe, if something starts to happen to the monochloramine, our ampermetric total probe is going to reflect that possibly more accurately than what you would see with the DPD. But as far as the solids go, we do have flushing systems. So we have systems specifically designed for pulp and paper applications. The larger ball valves, or not ball valves. Well, yeah, I'm sorry, they are ball valves in some cases, but larger valves to handle the higher solids, a larger flow chamber with larger fittings. Like everything is sized to be able to handle the higher solids. I'm not sure about going all the way up to 2%. I'd have to get back to you on that one. But yeah, we have several systems that have been sold, around the world for paper applications, for wet end monitoring chlorine level applications.
All right. And John was talking a little bit about the flushing system. I think that can sort of go into the next question. Well, the membrane foul and wastewater TSS, we have our amperometric installed in those systems. We have another flow cell. It's an auto flush, auto dump flow cell that does help keep that probe style clean in those systems. We also have a strainer valve. It's a 50 mesh auto back flush strainer that can help with some of those applications. So we do have cleaning solutions when we're looking at wastewater, both for the probe and for the sample going to the probe. Is there anything else you wanted to add on that, John?
Nope. Great.
All right, perfect. Can we install in a pipe? We don't have anything right now that installs directly into the pipe. And then I have just a couple more here. We have, what is the shelf life of a spare chlorine probe and membrane? As far as I know, the shelf life is indefinite on that cap. And what we look at is on those caps, when you do install a new cap, the T90, which means 90%, for it to come up to 90% of its reading, is 2 hours. Within 8 hours, we're definitely going to be at 100% of our reading. Mm-hmm. So sometimes if it's been stored on the shelf a little bit longer, it might take a little bit longer for it to condition and be ready for a calibration, but you are going to get that within a couple of hours. Does a chlorine concentration over the range of a sensor have any negative effects on the accuracy or lifespan of the sensor? The one thing that I'll say on that, the range shouldn't affect the lifespan unless we're looking at extremely low levels. We want to try to maintain an average of at least 10% of the range of that probe. So if we're looking at a 0 to 2 part per million probe, we want an average of at least 0.2 parts per million. 0 to 5 ppm, we probably want at least 0.5 ppm as our average. That's all I have on that. Was there anything else that you would have on that, John?
Well, yeah, I was just going to say, it's like for the free chlorine as an example, we have the 0 to 200 ppm probe. It uses the same electrolyte, same membrane, still has the 6-month life on the electrolyte. So unless you're talking really, really, really high levels, I mean, anything in the 0 to 20 range is not a concern.
Okay. Mm-hmm. All right. Looks like we have one more here. It says, will changes in flow in the service line lead to the amperometric free chlorine reader affect reading accuracy? I can go ahead. Timothy, you can probably handle this one. This is more about our atmospheric flow cell and why pressure changes or how pressure changes affect our probe.
Yeah, sure. I think that, obviously the changes in flow, if you did not have anything in place to restrict or monitor that flow, it can affect the accuracy of the chlorine probe. With incoming pressure that is extremely elevated, if you get a spike in the incoming pressure, it can raise the reading of the probe that might read inaccurately. Which is why we typically would recommend putting in some sort of pressure regulator. But when it does come to the open flow cell design or the vented flow cell, that is kind of a precaution that we take so that it would overflow off the top of that vented flow cell to prevent those inaccurate readings. So that is another way that Chemtrac's design just has it implemented and kind of is ready for inaccuracies or inconsistencies in the flow.
Yeah, I'll just add to that the venting, which he's talking about there is if there's too much excess flow, it certainly would flow at the top. But the other real important thing about the venting on our standard flow cell is we are ensuring that we're not transferring pressure changes directly to the membrane. So with a closed system, if you increase flow or increase pressure, 100% of that is pushing against the membrane. It's going to cause more chlorine to permeate through, and it's going to make your readings go higher. And then if your flow and pressure backs down, the reverse happens. With the vented flow cell, what we get is a small change in head pressure in that flow chamber. And if you get too much flow, like Timothy said, it will go, that's one downside, you could overflow it, but generally it's set so that it won't do that. But what you will see is small head fluctuations, but it ensures that we're not causing the full extent of that pressure change to be experienced at the membrane where it's going to affect your reading. So we used to have closed flow cells, and we had much more issues with maintaining consistent, stable readings. When we went to the vented design, it significantly improved it. So even though a vented flow cell is not great because of the potential for overflow, there are things you can do to prevent that, such as a dole valve, that will ensure you never have that problem. But the advantages of it are significant in terms of ensuring that we maintain a more consistent chlorine reading.
All right, very good. I'm going
Yeah.
to go ahead and wrap it up now. Again, John, Timothy, great job with all those questions. Thanks for getting everybody on that.
Great,
Just want to
thank you.
give everybody a quick reminder that this full recording is going to be available on demand soon, and we'll send a follow-up email with the link to everyone who registered. On behalf of Chemtrac, Timothy, John, and myself, I thank you all for your time and attention. We appreciate you joining us and hope you found this information valuable. Have a great rest of your day. This concludes our webinar.
Thank you.
Yes, bye guys.